I mean, I still have most of my stay left here, so I'm very excited to learn some more things while I'm here. So today I'll be talking about asymptotic symmetries in odd dimensions, and it's based mostly on these 3 papers that came out earlier in the year. And in the talk, I'll just be focusing on this paper, which discusses the simplest possible non-trivial case, which I think is the only thing one should talk about in a talk anyway. And then other technical generalizations of the things that I'm going to talk about are discussed here, and some more work that will be hopefully published soon. Okay, so I'm sure you know, but I'll give a brief review once more, a brief general history once more. So asymptotic symmetries are generically important, especially in GR, certainly when you want to define conserved charges and that sort of thing. But more than that, if you're interested in some sort of holography to describe holography, then presumably the first step is to study the set of asymptotic symmetries in the theory. Certainly, this is what we did for ADS. So now that we're interested in flat holography, we should also do the same thing for flat spacetime. And this study sometimes contains some surprises. In particular, it's not always the case that the asymptotic symmetries is the same as the isometry group of the spacetime that you started with. For instance, in ADS3, we know this, and it plays a very important role. And so this study was done first in the case of gravity by BMS, and they found something interesting, that the asymptotic symmetry group at null infinity. So let me back up. You need to specify several things to describe asymptotic symmetries. Firstly, which boundary are you talking about? ADS has one boundary, so there's really not much more to say. Flat spacetime has at least 5 classes of boundaries, and in particular, if I'm interested at null infinity, which is scri plus and scri minus, the asymptotic symmetry group there was studied by BMS in the early 60s, and they found an infinite dimensional symmetry group, which is what's called, well, today it's called the BMS group, and it consists of super translations and just Lorentz.
Just to understand the 5 boundaries, but you said at least 5.
Well, no, yeah, that was wrong. Yes, it's 5,
If you
exactly 5.
Null infinity, if you pass time-like infinity, and
space-like infinity. Yeah, not at least. That was incorrect. Yeah. Yes. So yeah, so here I'm describing asymptotic symmetries. Well, this is the asymptotic symmetries of GR, of general relativity, of any diffeomorphically invariant theory, defined in a asymptotically flat background. Yeah. In particular, here the particular boundary that I'm talking about is null. So people also talk about the asymptotic symmetries near spatial infinity, which is a whole different set. And depending on what boundary conditions you use, you in fact often just get the Poincare group. And there's sometimes what's called the SPRI group, which is a certain infinite dimensional generalization, which is basically very closely related to the BMS.
So another name would be asymptotic isometries. Be more apt to these. They preserve the metric?
They do not preserve the metric. They don't preserve the metric. They don't.
That's a silly question.
Yeah.
In a sense, are they, once you decide what the asymptotic behavior should be,
Yes.
Are they asymptotic isometrics? I
No.
don't suppose that's even the case in ADS3.
No, it's not the case in ADS3. So the definition of asymptotic symmetries is simply, first you have to define what you mean by asymptotically ADS or asymptotically flat spacetimes, which is the class of spacetimes that you want to work in. You have to define that. Which involves defining the fall-off conditions. Once you have done that, asymptotic symmetries is defined as the set of all diffeomorphisms which preserve those boundary conditions, but not leave in the sense that the coefficients can change.
Modulo those that are true.
So that's why. So one definition is allowed diffeomorphism divided by trivial diffeomorphisms. So allowed means everything that preserves the boundary, preserves the fall-offs, and trivial means everything that preserves the fall-offs and also preserves the coefficients of those fall-offs. So it's allowed divided by, modded out by things that go to identity. Those are pure gauge. In gauge theory, the asymptotic symmetries of gauge theories is now what we call large gauge transformations. Yeah.
Just one clarification.
Yes.
Which boundary we consider depends on the physical problem, right?
Yes.
Like BMS would take into account the gravitational radiation.
Exactly,
This way.
exactly,
Yes.
exactly.
But if you think in terms of holography,
Yeah.
it becomes a little bit confusing, right?
Well, in terms of holography, it is really null infinity that is probably the boundary that you want to study. So unlike in ADS, spatial infinity, nothing reaches spatial infinity in flat space-time. So that's not much happens there. Whereas all null rays reach Sky plus, and all time-like waves reach reach time-like infinity. So those are the two boundaries of interest here.
What fixes what the fall-off should be in general?
So as I said, that's more of an art than a science. You just have to find something that's self-consistent. There's no real, well, of course, the standard things, which is like finiteness of energy flux through Sky plus, finiteness of charges. All charges have to be finite. But then beyond that, it sort of depends what phase space you want to consider. And so you have to impose boundary conditions that are sufficiently interesting, but not too strong that it kills off interesting problems, but not too weak that you allow for crazy geometries that are not of interest. So it's more of an art. So this was studied in some detail in BMS's original paper, when then they established some.
The conclusions that you would draw would be independent of.
No, the asymptotic symmetry group depends crucially on these definitions. Yeah. In fact, I'll make a comment about this when I get to the higher D versions. There's some history to that also in higher dimensions. Okay. So this was the study that was originally done by BMS. They were expecting the Poincare group. They didn't know anything about ADS CFT. This is in the 1960s. So they defined. They presented a particular definition of. Yes.
Sorry,
Yes. Sure.
But, are your follow-off conditions necessary to formulate, to formulate a boundary term in the Einstein action and to make the action principle well?
Yes. Yes. So those are all the principles that one uses. Exactly.
And the follow-up conditions must be such that the asymptotic symmetries close under
Yes. Yes.
they form an algebra.
Yes.
So that was a very strong requirement for Brown and Yen.
Yes. Exactly.
For Brown and
Brown and no.
the,
Yeah.
ADS tree.
Because unlike isometries, which preserves the metric, asymptotic symmetries, since they don't preserve the metric, they don't generically form an algebra. So you have to find sufficiently. That's how you sort of once you find the set of asymptotic symmetries, then that's how you reduce it to find those subset which forms a closed algebra.
Sorry, but suppose you had the asymptotic symmetry group, suppose you had the follow-off conditions, and then you tried to weaken that, so to allow more
Yes.
general solutions.
Yes.
Would that be possible? I mean, would you be able to formulate a boundary value problem? Meaning
Yes. Yes.
you would be able to?
Yes. So.
What kind of physical processes would those describe?
Well, we now believe that the boundary conditions that are, at least for instance, what BMS did is really the weakest that you can.
The weakest.
Yes. Yes.
It should always be possible to strengthen because you can look at less.
Yes.
Yeah.
Yes.
It shouldn't be possible to weaken.
Yes. Well, the reason I was saying yes earlier is because in fact in higher dimensions, people did this exact same analysis and reached the conclusion that the asymptotic symmetry group of flat spacetime in any higher dimensions is only Poincare, which is reasonable. This is also what happened. Greater than or equal to 5. This sort of thing happens in ADS3 is special, but all higher ADS. But knowing what I'm going to talk about now, the fact that these asymptotic symmetries associate with soft theorems, which I'll tell you later about, and soft theorems are universal in every dimension, that would naively seem to tell you that in fact there must be these infinite dimensional symmetries also in higher dimensions. And in fact, then we realized that there's a way to weaken, at least in higher dimensions, the boundary conditions that was set by Wald and collaborators to include super translations.
But it cannot be further.
It cannot be further weakened. So for instance, there's no generalization of what's called super rotations.
Will they not form an algebra if you try to weaken it? Say weakest, what are the constraints?
Well, in principle, you could write down the weakest possible thing using precisely what Shiraz said. Often people just make additional assumptions.
Using what?
They just make additional assumptions, like certain fall-offs of the metric growth. You see, the real thing that you need to keep finite is often diffeomorphism invariant quantities, like the Riemann tensor. And so when you assume certain fall-offs for the metric, what I mean by you can weaken them is that you can weaken the fall-offs of the metric without affecting the fall-offs for the Riemann tensor or the Weil tensor, which means by which I mean the weaker part is they're all pure diffeomorphisms. But in fact, those pure diffeomorphisms are precisely the things that are related to these infinite dimensional groups.
But sorry,
Yeah.
the weakest possible conditions should follow from physics, right? Which is just finiteness of energy, momentum, etc. Should
Yeah.
lead to constraints, and nothing else should be necessary. That
Yes.
would be the weakest form.
Yes, like for instance, in gauge theory, finiteness of energy. For instance, only the field strength enters the stress tensor. So you can only really conclude what the fall-offs for the field strength are. So this tells you what the fall-offs for the vector gauge field is up to pure gauge terms. And if you set more pure gauge terms to 0, then you won't have any of these infinite dimensional groups. So then we can weaken the fall-offs of the gauge field, keeping pure gauge terms which don't affect anything in the field strength, and that'll give you more interesting physics. So that's sort of the way in which one would go about weakening them.
And that's how it works in gravity also?
That's how it works in gravity.
When you say these are as weak as they can get, you mean if you try to weaken them further, you need to have a...
You need to weaken them in a way so as not to affect the Weil tensor. So the Weil tensor fall-offs are as weak as they could possibly get. Yes.
Subject to physical conditions.
Subject to physical conditions. Now, if you want to weaken the fall-offs for the metric, you have to do so and not affect the ones for the. In which case, it simply means they have to be sort of pure diffeomorphisms at leading order.
You also have you also have to have a well-defined action with a well-defined
And well-defined action.
well-defined
Yes.
dimension.
Yes.
Maybe it's the same.
Yeah.
Variational principle. So the Gibbons-Hawking boundary. So you actually,
Yeah.
I should wait, but you actually erect a boundary towards future null infinity or past null infinity
Yeah.
at some finite affine time. And
Yes.
then
Yes.
Huh?
Yes.
Yeah. Gibbons-Hawking is a condition that you specify the asymptotic, the induced metric.
Yes.
Now you're not quite specifying the induced
It's
metric.
Dirichlet enough, but
Yeah,
not
but that
Yeah.
should be Dirichlet enough for this to be correct.
Yeah.
I see, but I was just trying to understand that you actually do the analysis by having a boundary at finite affine time.
Exactly.
Then take a look.
Exactly. Exactly.
Yeah.
This was this was discussed recently by Myers and Eric Pozza in the context of complexity equal to action. They study all possible boundary terms and with all possible boundaries and variational principle, keeping everything. So a proper analysis of this has actually been done recently. No?
I should just make one comment in
Yeah.
relation to what some people say. So Brownhill, of course, did their work much before ADS-CFT.
Yeah.
But
Yeah.
their fall-off after the discovery of ADS-CFT can be classified as a normalizable deformations. So
Yeah.
Brownhill fall-off condition is exactly to say that I am changing the normalizable mode size. Of
Yeah.
So that's very precise. Given ADS-CFT, we know this is as weak as it can
Yeah.
be without changing the theory. Thank you.
Okay. Okay. Yeah. So I was explaining what this is. So this is just an infinite dimensional generalization of translations. So a translation, as we know, is sort of just you just translate in some direction. And a super translation, it has nothing to do with supersymmetry. A super translation is an angle-dependent translation. So imagine so this is the asymptotic region. So you're sitting on the asymptotic sphere, which is often called the celestial sphere. And at every point on the celestial sphere, you do a different translation. So this is parametrized by a function, f of omega, on the sphere. And you do a different translation depending on which point I'm sitting on the sphere.
And the translation is like that.
No. So this is on the celestial sphere. So the translations are the L equal to 0 and L equal to 1 modes of this function.
The translations in which direction?
Along this
Oh, so this is translated along the null direction. Yes, very good, very good, very good. But not just, I mean, it's a full diffeomorphism space-time. At infinity, it's along the null direction, and then it does or whatever it has to do inside, which depends on the details of your metric. And the standard translations are the L equal to 0 and 1 modes, and L equal to 1 modes of this function.
Is this like a different choice of the affine parameter depending on where you are on the celestial sphere?
Yes.
Because anyway, the absolute normalization of the affine parameter is not fixed.
Yes.
So you can,
Yes.
okay, beautiful.
Exactly.
I see.
Exactly.
And absolute zero is not fixed.
Absolute 0 is not.
Absolute
So
zero. Okay.
so this is the
Can we
absolute
scale
0.
the affine parameter?
That's this thing here. That's the Lorentz part.
The translations are the zeros.
Is this zero?
Translation is shift in origin, and then the Lorentz transformation part is the rescaling.
You're right.
Yeah, exactly, that's exactly.
Okay.
Okay. So okay, this was done in the 1960s, but the people didn't really know what to do with it. So the conjecture it's not recent anymore. In 2014, the conjecture is that these symmetries should be thought of as symmetries of the S matrix of the theory. So quantum gravity S matrix, whatever that might be. Assume there's some S matrix which describes your theory, and so whenever I have symmetries, I have some no other charge, and the statement is that the no other charge corresponding to these symmetries commutes with the S matrix. So this is the implication of these symmetries. So this was the conjecture, and what we now know is that this statement is completely equivalent to the statement of soft theorems.
This is what I mean. This particular conclusion is independent of what you said about the falloff, right? That the symmetry should come into the S matrix. So maybe you have in mind the weakest, the symmetry group arising from
Well,
the weakest.
this is a conjecture. So yes, maybe the strongest conjecture would be you choose some fall-offs, you get some set of asymptotic symmetries, and then you conjecture that all of those symmetries, however weak they may be, commute with the S matrix, and you can obtain some.
But in order to get the biggest group there,
Yeah.
you would have to allow for the weakest of falloff.
Exactly. Yes. But it's not necessarily true that, well, we don't immediately know. The reason we know we have motivation that this conjecture is true is that they relate to soft theorems. But if you weaken them and you get more symmetries, you might get some junk that doesn't really make sense.
So this is not the weakest. This is the one that is. This is what
In 4 dimensions, it's the weakest. I'm only being very cautious. I don't want to say it's necessarily the weakest. I haven't done the full analysis. I know in 4 dimensions it's the weakest.
There is some canonical falloff which is nice.
Yes.
The responses of the.
Yes. Yeah. Whether that's the the absolute weakest you can do or not, I don't want to make any comment on that. Okay. So what are soft theorems then? So soft theorems is something you study probably in QFT1 in a QFT1 course. The statement is very very simple and very very general. So you have some scattering amplitude, and you have, let's say, one massless particle attached, and in the limit, when I take the momentum of this massless particle to 0, then a soft theorem states that you end up getting something that looks like the original amplitude. So this is the same original amplitude, without the soft particle. Soft just means low energy. Acted upon with some operator, which might be a differential operator, or it might also be a number. And this is called the soft factor. Okay, so this is the statement of the this is the form of sort of all soft theorems. Okay, so what I'm going to talk about today is understanding this side of the story in higher dimensions, in particular in odd dimensions. Because this side of the story is universal. It sort of doesn't even depend on the dimension I'm sitting in. In any dimension, the propagator is 1 over p squared in any dimension. So it's just really just some simple properties of what we expect of a quantum field theory that we can use to derive these soft theorems, and so they're generically true in all dimensions. So one expects based on trying to generalize this, is that there must also be some notion of these asymptotic symmetries in higher dimensions, more than 4. BMS's work was in 4 dimensions.
Sorry.
Yeah.
Pardon my ignorance.
Yes.
So when you say that the soft theorems follow from the symmetry, in precise form they follow from Ward identity, some kind of Ward.
Yes, that's right. This Ward identity right here. So if I take this Ward identity and then insert it inside any states, so there's an in state here and an out state, and set it equal to 0, then this is equal to this soft theorem. Yeah. So historically already this was slightly confusing because there are several papers by Ward which say that there is no super translation. So one thing you must know immediately, so let me tell you how the mapping works. We are thinking of this soft theorem as infinitely many Ward identities in the following way. This is a massless momenta, so it's parametrized by energy. there's an overall normalization, which is the energy, and then there's the unit vector, which depends only on the transverse directions, so on a point on the sphere. So in the soft theorem, I'm already taking energy to be 0. So this part goes away. So you can think of this soft theorem as one identity for every angle, for every point on the sphere. So that's how it matches up. So this is something that's one identity for every point, and you have a symmetry that's infinite dimensional generated by a function on the sphere. So in that sense, if I have a soft theorem, you should expect an infinite dimensional symmetry group. Now the problem was in higher dimensions, people expected that the symmetry group is just Poincare. So where is the super translation coming in? So this has been established now that there's a way to weaken the boundary conditions.
Suppose I take a graviton,
yeah,
and I let it go to zero wavelength, frequency,
yeah,
infinite wavelength.
yeah.
I look at that graviton and infinity. Does it affect one of these super translations?
Yes, yes. It induces a diffeomorphism.
Metric of eta plus a soft graviton.
Yes.
Is the same thing as what you would have got by starting with eta and applying a super translation.
Yes, exactly.
Thank you.
Exactly. Okay. So in higher even dimensions, this problem has been resolved by showing that there's a way to weaken your boundary conditions, and then you do the asymptotic symmetry analysis. You reproduce super translations.
Can I say
yes.
one more thing? So suppose I just think the problem classically.
Yeah.
Classically, the S matrix is the action as a function of data on scribe class and data on scribe class.
Mm-hmm.
And then you're saying that, well, if I perform a diffeomorphism, the action cannot change because the action is gated.
Yeah.
And therefore, if I change my data on scribe plus and data on scribe minus by diffeomorphism, the action cannot change.
Yeah.
But that adds a soft factor.
Yeah.
And that's
Yeah.
how it works.
Yeah.
Okay,
Yeah.
thank you.
Exactly.
This graviton that you create in this process, so it will have a polarization. I mean, it can have one of two. I can see that
Exactly.
going along the p direction.
Yes. Yes.
T plus r star, T plus r. But what's the polarization? So
Yeah. So I jumped. Yeah. Exactly. So there's a one-to-one map between everything that I've said here. So really, this you should think of this as one identity for every point in the sphere and for every polarization. So
where is the polarization?
well, this also has polarization, and then the soft factor enters. This depends on the
R
polarization.
also has the polarization.
No, but I thought Gautam was asking that in the super translation,
Yes.
where is the polarization?
Very good. Where is the polarization in the super trans? Excellent question. What happens, as I'll show you in the, I'll be mostly discussing gauge theory. This is much easier to work with, but is also true for gravity. The leading soft graviton theorem, which appears here, actually, even though it looks like there are d independent, let's say in 4 dimensions there are 2 polarizations for the graviton.
Yeah.
The soft graviton has only one polarization. There's an exact identity that the positive and negative helicity gravitons satisfy, so that there's really only one independent soft graviton.
I see.
This was very so there's only one function, but it turns out the subleading soft graviton, there's also a subleading, so I haven't told you what leading and subleading mean in this case, but what I mean by leading and subleading is that you can take this S hat and you can expand it in omega, and you get a structure that looks like 1 over omega S hat 0, of course, which is a function of epsilon and q hat, then plus order 1, and so on and so forth. So this is what I'm calling the leading soft graviton theorem. This is known to Weinberg in 65. And even though it looks like this depends on the polarization, in fact, there's only one independent S. We'll see that this is also true for photons. That we'll see explicitly. And here, this guy, there's no one independent. So there's actually a full 2 polarizations worth of symmetries here.
Or D minus 2 in general.
D minus 2 in general. D minus 2 in general. Yeah. Yeah. So 2 polarizations worth here, and that's related to the fact that this also gets extended, though BMS did not realize this, but in fact this also gets extended to the Virasoro, which is generated by a holomorphic vector field and an independent anti-holomorphic vector field. So these are the 2 polarizations, and they're each functions.
Wait, your discussion here is completely 4 dimensions.
Yes, at the moment just 4 dimensions. Yeah.
So
So
that's a generalization of the
yes, yes. So these are the two functions that give rise to this soft theorem, and that one function that gives rise to a single non-trivial, independent soft theorem that exists at this leading order.
So one way of figuring out what all these symmetries are is just take your graviton,
Yeah.
expand it in powers of omega,
Yes.
see if it generates effective diffeomorphisms at infinity,
Yes.
and those are your symmetries.
Yes. Yes.
About the fact that in the soft limit you have a connection between the polarizations, how does it check with the fact that suppose I take like a electromagnetism,
Mm-hmm.
which is fix a Lorentz gauge,
Yeah.
and then there's this observation that the zero momentum photon automatically satisfies del mu mu equal to 0. So there is actually a zero momentum longitudinal photon. So that seems to say that it's a single mode. I mean, it's not a field, but it actually adds to the number of polarization rather than subtract. This is the Polyakov story of.
I don't understand if del mu mu it automatically satisfies 0. That is 0.
Normally you use that to
Yeah.
get rid of one of the
Yeah.
polarizations.
Yeah.
Right, to replace one
Yeah.
component in terms of the others. But exactly at zero momentum you can't do that. I mean there's no equation there.
But then it's
Identity, right.
then, so yeah, I agree with that, but I don't then understand how it adds
So that
a degree
I
of
think
freedom.
sometimes it's interpreted as saying
Yeah.
that apart from the the usual left and right polarized waves, which are actually waves, depends on there's an omega and a p and relation between omega and p. There is an additional single mode which is at p equal to 0.
Shubir,
Yeah.
I think Polyakov may have missed this point. When you have k mu epsilon mu nu equal to 0,
Yeah.
take k mu to 0.
Yeah.
Okay. You don't miss that equal. There is still k hat mu. The k hat mu is still hanging around. So there is a relation in the limit of mod k going to 0.
I mean that is the real equation.
Yeah,
It's the k hat.
K hat mu epsilon mu nu equal to 0. So you do have the transversality condition even there. I know which paper you are talking about.
I see.
Anyway, no matter how you define this, I mean,
Yeah,
it doesn't
yeah,
matter how you define the soft limit, as in, it seems to be defined as first taking omega not equal to 0 and then taking the limit.
That
Yeah.
limit this doesn't.
That seems
Yeah,
like
yeah,
the
yeah.
precise.
Yeah.
So regarding this graviton hitting
Yeah.
the boundary and then doing a diffeomorphism, is it like if you take most general soft graviton and that gives you most general transformation most general diffeomorphism that you need to do on the boundary?
Yes, and that will be a super translation.
And then the first, power expand that in omega and give you the next one.
Exactly. This statement, by the way, well, it wasn't quite associated to the soft theorem, but this statement that you have a graviton that far out at infinity induces a diffeomorphism is known as memory, and it was studied like in the 70s. So it is like the what's called typically the third vertex of this infinite triangle. So you have symmetries. Just 1 minute. So you have symmetries, which means you should be able to measure these symmetries, perform experiments to measure them, and there's a well-defined experiment called the memory effect, which for instance, LIGO is set up for, but obviously doesn't have the precision to actually measure it. But there's a well-defined experiment that one can also perform to measure all of these diffeomorphisms. Yes, sorry, what was the question?
So the memory effect is what again? Just one.
So the memory effect, physically speaking, is the following. You imagine that, so let's think of it from the LIGO perspective. So you have two mirrors, and a gravitational wave passes by. And the way we know that a wave has passed by is that the mirrors start oscillating. The memory effect is after the wave has gone away, the net distance between the mirrors is now different from what it was originally. So even though it's not oscillating, there's a DC shift. And you can understand that entire DC shift as simply performing a diffeomorphism on the metric, which changes the way you measure distances. And that diffeomorphism is precisely a super translation.
And there's if all your clocks and rods, on Earth underwent the same change, how would you measure it?
No, it would be an angle. It's an angle dependent. Very, very good question. So in other words, what you're asking is if f was a constant everywhere, then you can't measure it. In particular, when I do super translations, only the L greater than greater than or equal to 2 modes of f are really the super translation modes. L equal to 1 and 0 are just standard translations and point. And yes, it's true. If everything gets translated, then nothing can be measured. But if there's a non-trivial angular profile, so in particular, as you're right, one LIGO won't work, but if I have LIGOs all over the Earth, then each of them will measure different changes in length, and then we'll have an angular profile of that wave.
The subleading theorem exists in all the dimensions?
Yes, so not just that, there's also, in the case of gravity, there's also a subleading.
In general dimensions?
In general dimensions, yeah. This and this are universal. They don't depend on any details of the theory, just diffeomorphism invariance. And this one depends on some higher derivative operator, some very finite term which have been classified. So we know, including all of those with some coupling constants, we know the most general form that this can take, but it's not entirely universal. But what has been shown is that even though it is not universal, it is still the Ward identity of a symmetry, in the sense that if I add higher derivative terms, the charges get modified accordingly, and the Ward identity accordingly gets modified in exactly the right way to reproduce the correct soft theorem. So this relationship, the fact that Ward identity is a soft theorem, seems to be very robust.
You say the symmetry is the same, it's just the charge that depends.
Symmetry is the same. The charge then depends on what I've done, or if I've added some extra terms, and then that modifies the Ward identity in some way.
This conclusion still holds only till subleading.
Yes, so there is no universal term beyond this. There's not even a factorization. The point is that there's an interesting factorization of this type that occurs, that you can always think of it as the original amplitude without this and acted upon with a certain differential operator. But beyond this order, that factorization goes away. So this is the story in the case of gravity. In gauge theory, you don't even have this. You only have leading and subleading.
Is there an analog of soft theorem in ADS?
Yeah.
In ADS.
I don't think so. I mean, ADS naturally has a IR cutoff, so I don't know what you would mean to take things to be soft in that sense. Because there's a IR cutoff.
EDS will work with boundary correlation.
So there's yeah.
Some limit of that.
Yeah.
It seems like it's what Gautam said, that the most general boundary conditions are those which only involve exciting normalized.
Yeah.
functions,
Yeah.
right?
Yeah. Okay. Okay. So now what I'm going to do is I'm going to maybe say some details. So I'm going to focus on this work done in this paper, which is just doing this entire analysis for gauge theories. Gravity is just carries an extra index, so you just have to worry about a few more calculations. But the qualitative features are all captured already by just doing a billion gauge theories. So what I'm going to now focus on is
Sorry, what is the infinite dimensional extension
yeah.
in higher dimensions of the rotation loop?
Good. We don't know. There's a symmetry. There's some guesses.
In
It's
principle, one can work this out.
you can work it out. There's some suggestions that it is well, there are two suggestions. One of them is that it's all diffeomorphisms on the sphere, on the celestial sphere. However, that does, well, I don't know what to say, but it seems that some of them are not normalizable, so it doesn't look like necessarily the right answer. Another option is that it's what's called divergent supertranslations. So there's these things called divergent gauge transformations for which the charges are infinite. So you don't have well-defined charges, but the Ward identities are finite. So you end up getting finite Ward identities. So in particular, for instance, for S1, which, in the case of the photon, the corresponding symmetry is a divergent gauge transformation, and the charges for that are all infinite, but the Ward identity turns out to be finite. And
There has to be something unphysical about them, because the
yeah.
DC shift will just diverge.
Yeah. It doesn't even satisfy the basic definition of asymptotic symmetry group. The DC shift takes you away from the boundary conditions. But it is still interesting that you get finite Ward identity and you reproduce exactly S1. So there's not a good physical understanding. Yes?
So, Prahar, but this kind of a thing is usually if you have a spontaneous symmetry breaking, right? Where you cannot define charges, but the Ward identities are there.
Yes. So yes, that is the guess.
So this
Very
says that there is a symmetry, but it's spontaneously broken.
Very good. Yes, thank you for that comment. Yeah.
But I had another question
Yes.
about this memory, statement about the memory.
Yes.
So there is this statement about whether there is realness in higher dimensions.
Yes.
But there's also a question of whether there is memory in higher dimensions.
Yes.
Do you know, like, how much you understand that question?
Yes, we know, we have understood memory in higher even dimensions. That's been completely understood, and it's been related to the soft theorems and asymptotic symmetries. I think this was relatively, I think, recent work by Strauminger and Monica Pate and Anna Roclario. But memory is not understood at all in odd dimensions. I'll make a comment about that if I reach that point. Yes, memory is not understood in odd dimensions still. Yeah.
And so the statement the work that you guys have done that says something about the memory in odd dimensions.
Sorry, say that again.
Is there some consequence, some statement that you expect about the memory
Yes.
from your work?
Yes, from my work, unfortunately, it looks like there is no memory in odd dimensions, which is the confusing part. From what we'll see is that, so memory is this DC shift, but what we'll see is that what we find is that exact component that gets shifted in even dimensions, in fact, remains constant in odd dimensions. So it remains constant, but it is important for the soft theorem. So we know that it plays some role, but it doesn't shift in the way that we think about. So yeah, I don't know how to resolve it. That's one thing I do want to do. Yeah.
Okay.
So I'm going to now talk about abelian gauge theory, the simplest non-trivial case, which is a U1 gauge theory coupled to massless charged matter. And I'm only going to talk about the leading soft photon theorem. So just large gauge transformations, not divergent large gauge transformations.
So if you started with, let's say, some event dimension,
Yeah.
and then compactified one of the dimensions,
Yeah.
you're saying that you should expect some drastic changes.
So okay, the crucial, I can already tell you immediately the reason for this. It's you can trace it all the way back down to Huygens principle. Huygens principle holds only in even dimensions, but doesn't hold in odd dimensions. So basically this is where
very sophisticated. That it assumes knowledge. Okay, you have to dumb it down later.
But is this
the propagator lies on the light.
the retarded propagator in even dimensions is localized entirely on the light cone, and in fact, because it's localized on the light cone, so a wave going through and it's localized on the light cone, so it induces a kink precisely at the point where it touches celestial sphere, and it's that kink that we measure in the memory effect. But in odd dimensions, the propagator is localized everywhere inside the light cone. So there's no real singularity, and it's very smoothed out. And by the time you reach null infinity, there's no kink, and so you don't see any. It doesn't affect the metric. So basically, the metric at the boundary in odd dimensions remains constant, a component of the metric, not the entire metric, but some component of the metric which is relevant for this analysis here basically doesn't get affected at all by any wave coming in, and so that's the problem. Yeah. Okay. Okay. So this is
the behavior inside the light cone is like a power law.
yeah. It's
so
one.
Let's say it's an exponential. Right?
Yeah. Exactly. Okay, so first to sort of tell you what's the issue in odd dimensions. So why have people done everything in even dimensions but are failing to do it in odd dimensions? Let's first go through quickly what happens in 6 dimensions, and then I'll try to just generalize that to 5, and we'll see that there's a problem.
Sorry,
Yeah.
Huygens principle is true in even dimensions.
In even dimensions, yes.
Even bulk.
Even bulk, yeah.
Here everything is bulk, right?
Everything is bulk.
Creating the bug.
No, but also if we were doing flat holography, the guess is that the holographic theory lies 2 dimensions lower. So if one is even, the other is even. So it's still, you can still make that call.
Or null, I thought it's not null, it's that
Yeah, the boundary of null. And it actually comes from, I recently, so in Myers' paper, they actually talk about all the boundary terms in various, so for instance, in ADS, basically the thing that gives you all the physics is the Gibbons-Hawking term, which lives in one dimension lower. But for instance, Myers shows that all this variational principal business on a null surface, there is no boundary action on the null surface. The boundary action is entirely localized on the boundary of that null surface, so scribe plus plus and scribe plus minus. So that's where all the physics must be. So it has to be 2 dimensions lower if I'm dealing with a null boundary.
Make one last comment.
Yeah.
Thermalization happens faster in even bulk dimensions than in bulk temperatures for the same reason. Send something from the boundary, just goes along with it.
There's a change between exponential and power law.
Yeah.
In simple systems.
Okay. So let me first tell you what happens in, I'm always going to use d plus 2 dimensions as the bulk dimension. So in 6 dimension, let's first discuss the 6 dimension story. So I'm going to work in, so this is Minkowski space. I'm going to choose 2 null coordinates u and coordinate r, which is roughly the size of the sphere. And the transverse sphere, which in the case of 4 dimensions, 6 dimensions is just S4, which in the case of S4, I'm going to parameterize using stereographic coordinates XA. So these are, the XA is like a flat direction. So the metric is just ds squared is minus du that's the metric of flat space time, and scribe plus is, this is scribe plus, so I'm going to only focus on scribe plus. Though of course to discuss S matrices you have to include scribe minus, but it's an identical story. And then scribe plus itself has 2 boundaries, scribe plus minus, and then 1 boundary there, which is scribe plus plus. So those are the only things that will be important.
This boundary from I0 and
Yes, these boundaries are different from I0. Yeah. That's why I tried to make it slightly separate.
And just to understand, boundaries are also in what, S4s?
Yeah, these boundaries are also S4s. All of these are S. Codimension 2. Okay, so I'm going to run through this very quickly. So the first step, I'm doing gauge theory, so we follow just exactly the thing I said. First thing to do is to define your fall-offs, to describe what the fall-offs are, and we're going to be simply guided by finiteness of charges and finiteness of energy, for instance. So for example, TUU, the electromagnetic stress tensor, roughly takes the form FUA, FUB, G upper AB, far out at infinity. So this thing, in order to have finite charge, must fall off like 1 over r to the 4, right? Because that's the S4 metric. And the G falls off like 1 over G upper AB, falls off like 1 over r squared. So this tells us that FUA has to fall off like 1 over r. So this is the radiative mode, in the sense that the part of the field strength that carries all the energy is the thing that goes like 1 over r. Of course, there's also Coulombic mode, which is going to be subleading, and that tells us how that mode couples to other particles.
The TUU is the energy flux.
Is the energy flux, yeah.
We saw that in Stanford's talk. Same.
Yes. So on null slices, you should talk about energy flux as opposed to energy on a slice. Similarly, you can do other analysis. I'm not going to bother, but you get the picture. So FAB, similarly, you can show falls off like 1 over r. And maybe the one that really will be of interest to me is FUR, the radial electric field. This falls off like 1 over r cubed. Now, this is not the Coulombic electric field. This is the part of the electric field that carries the energy. So it's the radiative mode. But there's also a part of this electric field that carries the Coulombic degrees. So it tells us how to couple, and that we can fix by looking at Gauss's law, or charge. So this charge we know is just integral r to r4 FUR, the integral of the radial electric field, right? So this tells us that the Coulombic part of FUR goes like 1 over r to the 4. So the radiative part is sitting here, and then there's a subleading component which goes like 1 over r to the 4, which captures, this component captures how the gauge field couples to all the other particles, charged particles in the theory.
These two powers would have been the same in 4 dimensions.
Exactly, which is exactly why I did 6. It's actually cleaner than 4. you can actually separate out radiative and Coulombic.
So Coulomb's law and radiation follow the same way in four directions.
Exactly.
Coulomb's law follows off faster.
Exactly.
than six then.
Exactly. Exactly. As a comment, this is exactly why the memory effect and all the other infinite dimensional groups were not understood in Waltz, because he assumed this fall off. You know what is given by the Coulomb's law, but in fact, if you include these higher these terms up here, this is where you get all the. Yeah, he didn't include all of the radiative pieces in his definition of the fall offs. Wald. Okay.
And this just follows from this analysis.
This just follows from this, very simple analysis. Yeah. Okay. So I'm going to relate everything to symmetries at the very end of my talk, but because it's easier to introduce calculations in this way, I'm going to start with what's called a matching condition. I'm going to conjecture a matching condition, and then do all of my analysis and show that corresponds to the soft theorem. And then I'm going to later show that matching condition is in fact the same statement as a symmetry. So you'll have to hold on to see why that's related to symmetry, but let's conjecture the following matching condition. I'm going to conjecture that FUR 4, and when I mean by 4 over here is just the coefficient of 1 over r to the 4. That's my notation. Whenever it's a bracket with a number in it, it's the coefficient of 1 over r. So I'm going to conjecture that FUR at scri plus minus is equal to FUR4 at scri minus plus.
So when you said in 4 dimensions the Coulombic and the radiative parts follow the same way, that's an artifact of this particular coordinates that you chose. Because I mean,
No.
So if I naively look at the electric field for Coulombic goes like 1 over r squared.
Yes.
And the radiative part goes like 1 over r.
No.
And
A goes as
But
one
yeah,
over
but
R.
Coulombic A0 goes like 1 over r.
no, what I mean is the power is let's say E times B. Both E and B go like 1 over r. E times B goes like 1 over r square, and
No, we can just do that analysis right here. Just if I was in 4 dimensions, this has to fall off like 1 over r squared. Well, that would not tell you about FUR. No, but it.
So the gauge field for A0.
Yeah.
both go
A0.
like 1 over r.
Just think of a spherical wave in gauge. It goes like 1 over r,
The Coulomb
and then
potential
the.
goes like 1 over r, and the radiation field.
Certainly true.
Yeah.
Actually, I was having a harder time doing it in higher D and understanding the different forms. That's me.
Yeah. Now higher D, I'll tell you, it's 1 over r to the d, and 1 over.
Square 1.
You square one and D. Thank you.
So these are the fall offs in.
For finiteness.
Yeah. Okay. So having conjectured this, well, I'll give you one motivation at least. Certainly, if I integrate both sides over the sphere, this is just a statement of charge conservation. Because if I integrate both sides over the sphere, this is telling us the incoming charge is equal to the outgoing charge.
What's the suffix 4 there?
Yeah, the 4 means that it's just the coefficient of this term right here. That's what I mean.
And so you're going to take that equality to be true?
I'm going to conjecture it for now, and I'm going to later show that this is in fact the same statement as a symmetry. But it's, yes.
And it would also be the same as that, the value of that at spatial infinity?
Kind of, up to this antipodal identification. So you can't really compactify compactifying spatial infinity screws things down. What you should really think of spatial infinity as itself, that's a cylinder, that's spatial infinity, I0. Scri plus minus is the future of spatial infinity, and scri minus plus is the past of spatial infinity. And the fields are matched antipodally in the sense that a field that has some value here goes around the sphere in the antipodal direction and then goes over there. And that antipodal identification is, so FUR is a function of U and R. I've already pushed out to scri plus minus, which is codimension 2. So this is only a function of X. And this antipodal identification is already there in the definition of my coordinates, which is why I chose these coordinates. The X at scri plus is antipodal to X at scri minus. So this, as it stands, is an antipodal map.
Sorry, one more question.
Yeah.
Since radiation is dominant,
Yeah.
its subleading terms don't interfere with this?
They do, but they vanish at square plus minus.
So
the radiation
key
terms fall off.
physical point is that radiation doesn't exist
Yes,
there.
exactly.
Then
Exactly.
it's clear.
Exactly.
Meaning the radiation should not be too near in the Penrose diagram.
Yeah.
Should not be too near this point. All radiation should come from finite thing and end at finite thing. And then it's sort of clear. Then it's just everything is Coulombic. And
Yeah.
what else could happen?
Okay. So then the goal would be, so this is my radiative piece. Notice that it's precise. It falls off as 1 over r, and it precisely depends on d. Well, in this case, a goes from 1, 2, 3, 4. It's a coordinate on S4, so it has precisely 4 polarizations. Those are the number of polarizations for a photon. So FUA in fact captures the 4 photons in 6 dimensions. And so what I need to do then is to take this equation and use equations of motion to relate it, to bring everything down in terms of this term over here. So this is where I have to use equations of motion. And so let me just tell you the appropriate, so of course equations of motion is Maxwell's. And so you take this equations of motion, write it out in these coordinates, substitute these fall-offs, expand just like you do in ADS, and then you obtain equations order by order in large R. And I'm just going to write down qualitatively the equation of interest. I'm writing these equations in AU equal to 0 gauge. That's a convenient gauge to work in. Okay, but this is essentially the equation you want. So the u derivative of this, precisely this field over here, is related to A1, which is the 4 photons, and Ju, which is telling us how it couples to matter. So it's just the matter current. So I can immediately obtain that by just integrating both sides of this equation with du. So then I get one term which is Fu.
What's del squared?
Oh, del squared is just the Laplacian on S4. Well, it's not. It's just flat space Laplacian. I'm working in stereographic coordinates. I just mean del A, with delta AB as the metric. Yeah. So I can just integrate this entire equation over u. Okay, and I'll get one term here which corresponds to FUR at square plus plus, and that's 0, assuming only massless particles. So in the far future, everything has to revert back to the vacuum, up to a gauge maybe, but that field strength doesn't see that. So field strength is 0 in the far future. And then I have and then the only remaining term is precisely FUR at square plus minus, which is what I want. On this side, I get a u derivative of the gauge field with no e to the I omega u. So this is precisely a soft photon. What would be a photon with energy omega? A photon with energy omega would be AA e to the I omega u integral du, right? The Fourier transform. This is what a photon of energy omega would look like.
Sorry.
Yeah.
FUR, I thought, I mean, that is anyway a boundary term, right?
No. This is the full FUR. Here, the one that's appearing in this conjecture is only the value of FUR at square plus minus. This is FUR on the entirety of square plus. FUR 4.
Isn't the u integral going to be between? Oh, I see. I mean,
Maybe.
I thought that du of that will give you two boundary terms.
Yes.
One I plus minus and the other I plus plus.
Yes, and the one at I plus plus is 0 because I'm assuming that only massless particles in the theory. So in the far future, there's no massive particles reaching square plus. So everything goes to 0. So you have to revert to pure vacuum. So the field strength has to be 0 up there. So the only contribution left over is the contribution from square plus minus. So this side, the left-hand side, after integrating over u, is precisely what I want. So I can then replace it with everything that over here. So I'm going to argue that this first term is the integral of u which is of this form, but omega equal to 0. So it's precisely a soft photon.
Magnetically charged particles?
You can have that, sure.
That will, no, not
That'll be a different matching condition.
Magnetically charged.
Um,
Three braces.
Yeah.
Sorry.
Yes.
Sorry, Prahar.
Yeah.
Can you just tell what the equation is? It's not very
Oh, let me.
visible.
Yeah, let me maybe write it out properly. So the equation, Maxwell's equations implies I missed something, JU4. Okay, so just to remind notation, whenever I have a curly braces with 4 with a number on it, it's just that the coefficient of 1 over r to that number. So this is the coefficient of 1 over r to the 4, the full coefficient. So this is a function of u and x. And well, this is the equation. So this is simply what Maxwell's equations tells us. So now what I'm going to do is I'm going to integrate both sides of this equation over u.
In some choice of slicing, is this Coulomb's law?
Yes, this is Coulomb's law.
But it's some straight slicing.
It's slightly more than Coulomb's law.
Okay.
In higher dimensions, you need slightly more than Coulomb's law. Okay. Okay. So when I integrate this side simply becomes FUR 4 at Scri plus plus minus yes.
If we put that index upper, then it's the u component of the equation, right?
It is, yeah. It's more than that. That's what I'm saying. It's a u including the r component, u and r component.
So you mix that.
You have to mix. You have to use both of them to get this. Yeah. Okay, so that's this side, and then over here I get okay. So as I discussed, this goes to 0. This thing is what I want, what I'm interested in, and I'm going to replace it with this. So the idea is all the physics that you really need is in here. Everything beyond this is just technical details. So the integral of dua, I can think of this as multiply by e to the I omega u, and then take a limit of omega goes to 0. So this is precisely a soft photon. In Fourier space, u is a time coordinate, so this Fourier transform is the energy, and then I basically take a photon of energy omega and then take an omega goes to 0 limit. So when I take this, so what I'll eventually do is I'll take this equality, this equal to statement, and I'll insert it inside an S matrix. So this term inserted in an S matrix will precisely give you the soft the left hand side of the soft theorem, where you take a soft photon and take a 0 limit. No.
What is the relation of TU with the soft term?
None. That was only used to find the fall-offs. Yes, this is J, because I'm talking about gauge series. It couples to the current,
Right.
not to the stress
So
tensor.
the soft term, what is the gauge invariant way of writing that term? Is there any?
Well, in reality, you should probably think of this as integral du u FUA. And it's integrating by parts in u that then gives us this, but you don't need it. This is the gauge invariant way. Okay.
So you're
yes.
going to make a switch here between real space and momentum space, I guess. A of 1.
Yes.
That's a function of that's a function of u in that way and of x.
Very good. It's x in position space.
That with
Yeah.
k hat, no?
Yes. So that's an extra step. I'll do it. I'm going to do it in detail in even dimension. I'm just trying to tell you what the issue is. Well, the general structure, and then why this doesn't generalize to 5 dimensions, for example. And then this operator. This, by the way, is the light ray operator that we were talking about. It's precisely the integral of j minus over x minus, like on a null surface. So you have these. This is the sense in which a light ray operator naturally appears, and then the action of this quantity on a state is the thing that's giving you the hard charge.
That is the charge flux.
This is the charge flux through Scri plus, exactly.
Let's say the last thing again, the action.
So this is the light ray operator. So the action of this operator on the states is precisely giving you S hat, which is the soft factor. So then everything else beyond this is details. You have to actually show that this gives you S hat and everything works. But I'm going to focus on odd dimensions. But anyway, this is the way one sets up the problem.
Sorry, again to you.
Yeah.
What if you insert u du integrated? Just in this formula instead of writing ua?
The formula is whatever I'm getting from the equations of motion.
Right, I'm asking
Yeah.
that if you insert this operator, then
Tu, yeah,
and then multiply with u and integrate over u.
that's a subleading soft graviton theorem. That's associated to a totally different soft theorem.
Okay, so
This integral du theorem is the analog of what you are asking.
If I was doing this entire analysis with the subleading soft graviton theorem, then I would end up with, roughly speaking, the light ray operator that looks like TUA integral du minus del A integral du u duu.
and then even for subleading,
Yeah.
what will be the coordinates slightly like you know why I'm asking
Yeah.
this, right? Because I want to know the transverse coordinate of uu.
Yeah.
What is the relation with the photons? So how does that map?
I'm not following that question.
So TUU
Yes.
sits at a point which has a sphere and the direction in the null direction.
Yes. Yes.
So I'm calling the sphere as transverse
Yes.
direction.
Yes.
Now you said this is related to subleading soft photon.
Graviton theorem.
Subleading soft graviton theorem.
Yes.
And then I want to know the location of this TUU in the transverse on the sphere. How is it getting related to the polarizations of those gravitons?
Polarization is sitting in A. And the x is the direction of the graviton.
And what happens to this? So what is the information about the sphere in TUU?
All of this entire thing is a function of x, right? It's a function on the sphere.
So if I have two of these inserted, sorry, I am going.
Yeah, if you have two of these inserted at different points, then it's two gravitons pointing in different directions.
Different directions. So,
Yeah.
So all information about the sphere where this TUU is related to which direction these photons are.
Gravitons are pointing.
Okay.
Yes. Yeah.
I'm really sorry.
Yeah.
Missed the structure. So just to understand, so the left hand side, as you said, gets only support from FUR scribe plus minus.
Yes.
term.
Yes.
Just to understand, and then you are trying to prove which statement?
So I'm trying to prove the soft theorem. I'm trying to prove. So I start with this, and I insert this statement inside an S matrix.
Inside an S
Okay.
matrix.
So now I want to manipulate both sides and bring it into the form of a soft theorem. And remember, the soft theorem form was that I have some amplitude, and there's a soft particle, and then I take a soft limit, and I get some soft factor times this. So this is the form. I want to show that this statement is equal to this statement. So the way I do it is I find an equation of motion. And this is the equation of motion. You start with, you can show with Maxwell's equations. This is derived from there. Now I take this equation and I integrate over u, both sides over u. The left hand side gets, as you said, one contribution from scribe plus plus, one from scribe plus minus. This goes away, and this. So then I basically get an equation. This is equal to something else. So I can then, in this equation, I can replace everything that I see here with everything on this side.
Yes.
On both sides?
On both sides, yes.
I mean that,
So this is on scribe plus minus, so this gets replaced there, but there's also an analogous equation for scribe minus, and then I get something else over there. So then that statement becomes the equality of this is equal to its corresponding quantity on scribe minus. And I want to simply show that at least qualitatively, this first term is the left hand side, and this second term is the right hand side. And the way you can see that is that this first term, you can think of it as, because it's an integral of u over u of a, I can think of this quantity as you multiply by e to the I omega u, and then take a limit of omega goes to 0. So what you're doing here is taking a Fourier transform of a linear gauge field, which in energy omega. So this inserts a photon with energy omega, and then I'm taking an omega goes to 0 limit. So that's a soft photon. And then this thing is the current. So it tells you how it couples to all the other charge fields. So this has some action on states, which you can work out. In other words, I'm saying integral du Ju on a state psi is S hat on a psi, on psi. This you can work out given the form of Ju. And so the claim is that when you go through all the details, that this S hat is the same as that S hat, and you end up getting something that looks like a soft theorem.
The two terms are differences between, because you've done it on the left.
So a soft theorem, this S hat includes in particles as well as outgoing particles, precisely with a minus sign. So that minus sign is coming because it's
But
coming in
the
also.
left hand side also works out.
Yes, yes.
Left hand side only one guy, right? So what is the
Yeah.
log of the difference?
Yeah, so this is a slightly more technical. In fact, it's actually both sides. If you really look at, if you go back to what you really compute in an S matrix, is the insertion of, you really insert A out minus A in, if you remember. So, and similarly, and then this is the thing that you then replace with phi. It's A out minus A in, that is actually you're computing using Feynman diagrams. Also precisely this thing here.
And
what-
And of course, the idea is, when I do a time ordering of this, the A in will go hit the vacuum and it'll annihilate it. So it doesn't really contribute much. But it's the insertion, the operator that you're computing is this form here.
And the soft graviton then that you draw is actually the insertion.
Is the insertion of this quantity.
I think in Feynman diagrams, that soft graviton could have had either positive or negative energy.
Yes. Yes, exactly.
So it could have been either from the inside or
Or from the
all
outside.
options.
And then you allow for that and then take the omega.
Why is the matching condition equivalent to the statement of symmetry?
Let me do that when I get to the odd dimensional case, because I'm definitely running out of time. Huh? So now let me tell you. Okay, if I was to try and do the same thing in odd dimensions, this is what's going to go wrong. So let's do the same analysis here. So in odd dimensions, let's say in 5 dimensions. So 5 dimensions is d plus 2 equal to 5. So FUR in this case falls off like 1 over square root of r. The radiative piece, FUR doesn't, so it's FUA. So this falls off like r to the 5 halves. Yes. And the Coulombic piece falls off like 1 over r to the r cube. And so you see the problem immediately. The radiative piece is at half integer order, half integer power, but the Coulombic piece is at integer power. The equations of motion are completely analytic. There's no square root of r in Maxwell's equations. So you can never find any equations of motion that relate this coefficient to that coefficient in any way. So this is the fundamental problem. So that basically it's telling you that certainly in odd dimension equations of motion are not enough. It's not going to tell you how to relate these two coefficients.
Sorry, why was it that what you did was relating the Coulombic piece?
Well, I'm starting from a matching condition which relates the Coulombic piece, FUR4, which is this coefficient. And then I look for an equation of motion which then transforms this 4 to a 1, to FUA1. And here I can tell you FUA also falls off like, the radiative part falls off like 1 over square root r. But in odd dimensions, there's never going to be any such equation of motion. So you can't do that. So it's not going to work in this way. So how do we fix it? So clearly we need somehow more information than equations of motion. We need to use more stuff. And then the question is, okay, if we have to use more stuff in odd dimensions, why didn't we have to use that in even dimensions? Somehow that was automatically satisfied, perhaps. Okay, so the hint that we get is almost immediately clear if we just look at some stuff that I suppose you'll all be familiar with in very, very basic ADS physics. So think of a scalar field in ADS, let's say a free scalar field, phi. It satisfies a second order differential equation. So it can only be solved up to 2 constants. And the equation of motion will never be able to relate those 2 constants. And those 2 constants are something like phi naught z to the delta plus like a z to the d minus delta, and then plus, of course, additional terms. And equations of motion will never fix phi naught and a for you. They'll never relate these 2. But of course, we know that the data, well, in a normalizer, this is the only data that you have. And then this is fixed in terms of that. How do we fix this? This is fixed by regularity. So that's what I'm going to use. I'm going to use the fact that you do a large R expansion, but you have to insist that the expansion is then regular. inside. So r equal to 0 somewhere inside. So in that location, I need the field to be 0, and that's the thing that's going to give me an extra relationship between.
How does this play out in even dimensions?
So in even dimensions, it turns out, as we'll see, regularity actually does require you to add extra terms, but none of those terms, including logs and various other things, but none of those terms affect the soft discussion. So we were lucky, I think, in even dimensions that it worked beforehand. Okay, so that's what I would like to do. So how do I actually go around doing it? So really the easiest way to do it is to just start with a solution that we know is regular, and we just expand it, and then we just look at various terms. So what's a solution that we know is certainly regular everywhere because of the definition? So so let me now describe that. So to do this, I'm going to shift gears slightly and find the solutions in the following way. And I'm going to break the field strength into a radiative piece and a Coulombic piece. And what I mean by this is that the radiative piece is something that satisfies free equations, and the Coulomb piece is fixed using a choice of Green's function. So in particular, I can say f mu nu C is integral of g x minus y. This is now in Cartesian coordinates. Let me use capital.
A particular solution and a homogeneous.
Exactly. And this is so that's my solution, and this is the standard scalar Green's function. So we know that this is a totally nice solution everywhere. And we already know a solution to this. It's the mode expansion. That's completely regular everywhere. So we'll take a mode expansion and expand it. That's how we'll know what the various terms over here are. And then we'll just assume that the current is nice and regular everywhere. So it has a well-defined asymptotic expansion. And then we'll use this to expand the Coulomb field. So having done this, this will sort of by construction be regular. And then we'll just know what all the large R fall-offs are. And of course, equations of motions are also already satisfied by hand. Okay, so
So isn't this what you had done here, this analysis? What was the...
Well, the difference here was that I solved equations in a large R expansion, which can fix some of the coefficients, just like in ADS, but after all, it's a second order differential equation. So 2 coefficients are going to be unfixed. And so then we'll have to relate them using regularity. Okay, so let's do that. Okay, so this one I'm just going to tell you for lack of time. It turns out that there's nothing fishy about this. So this is, in fact, in order to obtain the Coulombic field, we could have just done the large R expansions. It turns out it works perfectly. So all this large R expansion business that I was doing, it works perfectly for this mode over there. So in particular, the equation that's of interest is going to be FUR D. I'm going to use C. C just stands for Coulombic, and D stands for the coefficient of 1 over R to the D. I mean now in D plus 2 dimensions. And this is just equal to E squared JU D. So this is the equation that I have from expanding this Coulombic piece. The radiative piece is slightly trickier, but let me run through this. So F mu nu, so in Cartesian coordinates, roughly has the form integral, d plus 1. Then these are my creation operators, I qx, right? Oh yeah, that would be okay. So the first step is to go into my UR coordinates instead of Cartesian coordinates, and then I'm also going to use, so to first simplify this just by changing coordinates, I'm going to use this parameterization for my momenta. Which is basically a generic, and then this simplifies to d omega d minus 1 d dy. Then I have a term that, and I'm now just focusing on FUR because that's the only coefficient that will be of interest. This becomes del A OA U minus I omega R x minus y squared plus complex conjugate. Okay, so let me just explain the qualitative features. Maybe I think I'm missing out. Overall 1 over R should be there. Let me just check. I just want to show you all the large R fall-offs.
So here you are calculating the flux of a nice wave.
Yeah, so this one I'm just solving the free equations of motion. So this is just solved by mode expansion. So as I've done, I've separated into free at Coulombic.
So
I've already handled the Coulombic piece
the
here.
previous constraint was the finiteness of energy. through
Yes, yeah.
But that is not realized by any.
Well, mode expansions already contains all of that information. It's already finite energy, so everything is already nice with that.
But it would presumably go slower than what?
No. It will go exactly as fast as expected, except that it will contain a piece, this radiative piece, which is the thing that's carrying energy. It will contain a piece that goes like 1 over square root r, or whatever the half integer power that we expect from the fall-offs, but will also contain pieces that have integer powers, which is required by regularity. And those integer powers is then the only thing I need. And once I figure out what those integer powers are, then I'm done.
And you couldn't have argued for that integer power by staying directly aligned, scribe class.
No, because you have to use regularity. You have to really know what's going on. Yeah.
Interesting.
Yeah. So I'm just going to tell you, show you where the two powers are coming from.
The Green's function?
No. The Green's function is the Coulombic piece. Yeah. So it's not even there.
It's just property of the large R expansion of some Bessel function.
Yes, exactly.
It's not that it comes in integer and half integer powers.
Exactly. Exactly. In fact, now that we've this analysis, basically it turns out, I'm not going to show it now because for lack of time, but you reach a stage where you basically get the exact expansion for a scalar field. So you can really, ADS, scalar field in ADS. So you can then really relate everything I'm doing here precisely to everything known in ADS. So
because if you solve in spherical coordinates, you solve for plane waves very fast.
yeah. And so in particular, so I'll make a comment quickly, but let me just show you the quick fall-offs. So remember, I'm interested. Oh, this is not x minus y.
Actually, I didn't know this. The Bessel functions have. Okay, thank you. Thank you.
Yeah.
Regularity with particular Bessel function, we should have this particular ratio between even and odd. Even between
Yes.
fractional and.
I'll explain.
Bessel functions in even dimensions, is it right that they basically something kinds of terminating polynomial?
No. The Bessel, for instance, in ADS, the Bessel functions that appear are k nu, where this nu is, d squared by 4 plus n plus m squared. So it's any random thing.
No, but suppose we take massless waves in flat space.
Yeah, exactly. So massless waves in flat space, the Bessel functions that you get is also k nu. In even dimensions, nu is an integer, and in odd dimensions, nu is a half integer. Is roughly proportional to d over 2. And you see when the Bessel function has half integer expansions, it's just a full expansion, contains terms that involve z to the nu as z to the minus nu, and then just a whole bunch of terms.
Yes.
When nu is an integer, you get, in addition to these two terms, you get, in addition to these two terms, you also get log singularities. Yeah, so in ADS, for instance, these log singularities appear for special cases of masses, like a massless scalar in odd dimensions. Then you have these things called conformal matter anomalies, and they play some role.
So I was going to ask whether there's a connection to anomalies here.
Yes, I suspect. It's not been explored, but yes, given what we know from ADS. So we see in even dimensions, there have to be these additional log terms, which for instance, we wouldn't know if I assume a large R expansion. There's clearly non-analytic. I didn't tell you what Z is. In the case of here, Z, it turns out to be U over R, square root, right? So in the large R expansion, you get log divergences also.
And in odd dimension, the large R expansion, does that you get an e to the power I something?
No. No, it's exactly this, and a full expansion. This is near Z equal to 0, remember. Z equal to infinity, you get some E equal to.
Near infinity,
yeah.
Near stripe plus, you get some oscillation.
Yeah, yeah. No. Z equal to 0 is square plus.
Well, a wave oscillates, doesn't it? You're probably taking that out. Pi omega.
The oscillations would be in. The oscillations would be in. Yeah.
And is that the remaining thing are terminating?
No. None of these are terminating. One of them is, I think, the coefficient of. So in the case of even, one of these is terminating. I can't remember which, and then so it's terminating. You get Z to the nu. It's terminating, and then it's replaced by various log terms, and then this is infinite. This is infinite. But apart from that, there's no terminating.
So when you take the soft limit, this fractional, this half integer part goes away for the FUR.
This one, no, it is actually what we need to get the soft theorem to work. Well, this is an odd dimension. So in odd dimensions, all of the things are half integer. So they don't.
Your argument was that you don't want half integers.
Not that I don't want. I want half integer will always be there. That is needed by finite. I want an integer part, which is I also want an integer part. And the point is, it's precisely you get one term which is Z to the nu, one term which is Z to the minus nu, and Z to the minus nu gives you the half integer pieces, and Z to the nu gives you the integer pieces. Literally just like how it works in ADS. Yeah, so then these two are related, and it's precisely this coefficient which is the radiative mode, and this leading coefficient which is the Coulombic mode, the analog of phi naught and A. So there's a lot of similarity, which we expected on general grounds, but this is maybe more cleaner. So let me at least quickly tell you where these two terms are coming from. These are more details. I don't have time to go into this, but what I now want to do is I want to take a large R limit of these two things, right? So the only R appearing is over here. So I can just do a large R limit by doing a stationary phase approximation, right? So this guy, when R is very, very large, it gets dominant contributions for when Y is equal to 0. This is what was studied previously. So when Y is equal to 0, I can just do a Taylor expansion of this thing near Y equal to 0. And you can immediately see, so then I'll just get various powers of Y over here. And just by dimensional analysis, you can show that you'll get half integer powers. Because when I do an expansion in Y, I get something like YA1, YAN. But if n is odd, the integral is 0 by just Y goes to minus Y symmetry. So n has to be 2n, n has to be even. And then I can just do dimensional analysis. I can scale Y to 1 over square root of R. Then I get a 1 over R to the d over 2 from the measure here, and I get just d over 2 plus n. And then the overall R sitting over there, so d over 2 plus n plus 1. So it's and then sum over n positive, less than or equal, greater than or equal to 0. So it's precisely the right expansion that you expect from these radiative arguments. Okay, so this is great. But in fact, there's also another term which we didn't. This was not understood or studied before. There's also dominant contributions from when omega equal to 0. But that's exactly what we are interested in, right? So that is the thing that we should really be looking at. So when omega is 0, we can then expand this in omega. And then let's just quickly look at the coefficient that we'll get. So then I can also again do this at leading order. This falls off like 1 over omega as a pole. So then let me just rescale everything and quickly see. So if I rescale omega, again just do dimensional analysis. From this thing, I get 1 over R to the d. And then there's an overall factor of R outside. And then there's a 1 over omega, precisely 1 over R to the d, which is exactly the matching condition in d dimensions is Fd. So it's precisely this omega equal to 0 contribution in this large R limit that is capturing the power that we want. And now we have to be more precise about this because we have to keep track of factors of 2. And the way we do that is we just assume that this guy over here admits a soft expansion in omega and a Fourier expansion in x. Then we do explicitly the u and y integrals, and we get precisely the Bessel functions. And then we just expand the Bessel functions and the Z new one. Okay, all of that is details, and let me just write a couple of more formulas.
That's the Coulombic field then?
This is the radiative field. The Coulombic field is here.
Yeah.
I haven't dealt with it. Well, I've dealt with it.
The that you got, the follow-up that you got was like that. Was like a Coulombic follow-up, right?
No. It was both, right? It has two contributions. One from Y,
Yes.
so that gives you contributions of the form 1 over R to the
Yes.
d over 2 plus 1 plus n.
Yeah. And the other guy?
So this is there. So this is radiative. And then you also get terms that look like 1 over R to the d plus n.
And the coefficients are directly.
And the coefficients are directly related.
And that you could have just seen by taking radiation fields and expanding Bessel functions, right?
Yes.
Without
Yes.
anything else.
Without anything else. Yes. Yes. So
There's a fact about Bessel functions.
it's exactly.
Sorry,
Yes.
so this is a K function or what Bessel functions are we talking about?
Bessel K. The Bessel K function.
All these are Bessel K.
Huh?
And we are related various coefficients in the series expansion of the Bessel K functions. Is that the statement?
Yes, exactly. That is right. That's right.
Okay.
That's right. So in particular, yes.
So this if you are having even dimensions, then the Bessel K is truncate. Even space-time dimensions, the Bessel K is truncate.
No, they don't truncate. You get log divergences.
I mean, up to an exponential factor. There's an exponential factor and then they truncate.
Maybe we're not following. It's Bessel K with a particular nu, and in even dimensions, the order of the Bessel function happens to be an integer. So, and then it's a standard Bessel function with an integer order, so it's still an infinite expansion, but now it additionally has log divergences.
I thought even space-time dimensions, I thought the Bessel K used to be of a half integer. And even you have half integer.
No. These are not Bessel. The Bessel K in I think 3 dimensions, but with even or odd order. That's what's appearing. In even spacetime, Minkowski spacetime dimensions, the Bessel functions that appear are the standard Bessel functions with even standard Bessel functions with integer order, and in odd spacetime dimensions, you get the standard Bessel functions with half integer order.
So this I don't understand. Let's say 2 plus 1 dimensions. Okay.
Yeah.
You get K naught and the standard Bessel functions with this, integer orders.
In ADS,
2 plus 1
in 3-dimensional ADS.
No, in 2 plus 1 dimensional flat space. If I just solve electrodynamics in 2 plus 1 dimensions.
Yeah.
Okay, I get like K naught, and this is a cylindrical topic. These are the cylindrical Bessel functions, which are the integer order Bessel functions.
Those are.
And in 3 plus 1 dimensions.
Yes.
We get central Bessel functions, which are half integer Bessel.
No. I think we are talking about.
Right.
I don't think we're talking about solving Bessel function in various space-time dimensions.
I
think.
Static problems or radiation problems?
Yeah.
But it doesn't matter, right? It's the same thing. I mean, I thought it doesn't change. Whether it's integer order or half integer order does not depend on whether you're talking about radiation or static problems.
So I'll have to think about that. I can tell you just what's happening here. If you're sitting in odd dimensions, I'll tell you the order of the Bessel function is d over 2 minus 1. So that's what I'm finding.
Yes. So
yeah.
the D is what? D is in space dimensions usually. In the number of phase dimensions. D by 2
No. Sorry, in my notation, it's d over 2 minus 1 where the space-time dimension is d plus 2. So in 4 dimensions, you will get k0. And you don't get just one Bessel function. The point I'm trying to make is that you get a whole series of Bessel functions, which is with order d over 2 minus 1 plus n, where n is a non-negative integer. So you get this whole sum over.
Yes.
Yeah.
So that is fine. So maybe let me just rephrase the question.
Okay.
One is that, does this order, whether it's half integer or integer, does it change when you variable separate in a different way? Is that the reason why this change is happening? So at least if you variable separate it along the usual time,
Yeah.
and conspective coordinates.
Yeah.
Like I mean, at least it works in a particular way, but the way that you're saying is opposite.
Yeah, I'm certainly
confusing.
variable separating in a different set of coordinates. I'm variable separating in these UR x coordinates that I've been working in. So I separate in x, and I write down equations in u divided by r. So maybe that's the difference. Yeah.
Okay.
Okay.
Okay. Yeah.
Okay. So I've told you at least qualitatively how it works, but let me at least write one or two equations more. Okay, so what you find with this is that FURD is, so for instance, in odd dimensions, you'll get something that looks like ddy del A OA over x minus y squared to the d minus 1. So this is in fact just like a shadow transform. This is the shadow transform of that operator. This AA0. So again, OA0, I mean this is the coefficient of 1 over omega. So it's the thing that gives rise to S0, the soft factor. So this is precisely, when I'm talking about the leading soft photon theorem, I'm talking about insertions of this operator over here. So this is exactly the shadow transform. More than that, I should say also this is 0, so it only depends on x. So O, which is the annihilation operator, depends on the momentum. So it depends on omega and y, which then localizes to x when I take the large R limit. So it depends on omega and x, and then I'm taking a soft expansion and extracting the coefficient of 1 over omega, so it depends only on x. So interestingly, this doesn't depend on u. Remember, this is the full thing, so it should in principle depend on u as well as x, but it doesn't. And this is an indication of this Huygens principle that I was telling you about, that far out the radiation goes all the way out, but it doesn't, this value of this particular Coulombic mode doesn't get affected at all by whatever is happening. It just remains constant throughout. On the other hand, in even dimensions, as I said, you're going to get log divergences. So you get terms that are order 1 over u that I don't care because I'm only interested in what's the value at large u. You get exactly this term. And I should really say it's the complex conjugate. So there's an I plus complex conjugate. No, there's no I there. So there's an I here. In particular, that means that notice that because of the presence of I, the complex conjugate, there's a minus sign here, whereas there's a plus sign there when I do the complex conjugate. And then there's a log divergence, which is also proportional to precisely del A OA minus the complex conjugate. And then there's this term, which is the important term, which is theta of u minus theta of r. Theta is the sine function, which depends on del A OA plus complex conjugate. So this is the only place where the plus appears. Everywhere else it's a minus. So maybe I should, let me remove the I and say minus complex conjugate here. Okay, so first and foremost, we must remove this log divergence. If you want to evaluate FUR at square plus minus, we have to ensure that there's no log when this is a well-defined quantity. So in particular, I must impose boundary conditions which sets this to 0. So in particular, the complex conjugate here is OA dagger. So this tells us that OA has to be equal to OA dagger. Again, remember this is in the soft mode. So there's no, as Shiraz was saying, there's no plus omega minus omega mode. It's just, there's just one mode with the minus sign. So that's one thing. Another thing that immediately you see, because if I impose the boundary condition that kills this off, it also kills this piece off. And this is important because remember, shadow transforms, if you've read some CFT, they're not really well defined for operators with integer dimensions, in even dimensions, because roughly speaking, you know, in the shadow transform, this coefficient, you get terms that look like gamma of delta plus d over 2, delta minus d over 2, gamma of d over 2 minus delta. So if d is an integer, if d is even and delta is an integer, then one of these two is a negative integer and the gamma is not defined. So it had better be, in order for things to be finite, that this term goes away. So setting this to 0 nicely also cancels that thing. And it secondly shows another thing, that there is a kink. Precisely, you see at theta, this is theta of u, so it's the sine function of u. So as the field goes from u negative to u positive, its value changes. In particular, theta of r. So r is always positive. On square plus, r is positive. So this is just really just theta 1. So, was it? Yeah. So when u is positive, this is just evaluates to 0. So this tells us that FUR at square plus plus in the far future is 0. This is Huygens principle, that everything just goes along the null direction, and then once everything is gone out in the far future, things just are 0.
But it's theta of u, not delta.
Theta of u, yeah.
So it's the stuff that comes inside, rather than, I mean, right? I mean, is this the stuff that says that the propagation is not exactly along the light front?
No. This is an even dimension, so it is exactly along the light front.
So why is it theta of u? Why is it is delta of u?
Well, it depends on which coefficient you're looking at. So FUR is constant, and then a wave comes in, and then it goes to 0. So propagation happens. So yes. So yeah, maybe theta of u is the sine function. So let me just write it. Sine of u.
Theta of u is minus 1.
Yeah. No. This full thing is the sine function.
This is what you get. Say theta of u is this.
Yeah. So you should think of it in this way. So FUR, nothing is happening. FUR is just constant. Suddenly a wave comes exactly at this point, and then it becomes 0 straight away after that. So there's a kink. It jumps exactly at the point when the wave comes in. But you see, in odd dimensions, it's constant, and the wave comes in, and then nothing happens. Basically, because there's no kink at one point. It's like sufficiently spread out that it really doesn't affect by the time it reaches square plus. Okay, that was just an observation. Okay, but you see that it's the right term that's appearing. I'm interested in FURD. So I get precisely this term over here, which is exactly the term that's giving rise to the leading soft photon theorem. And then the Coulombic part is just manipulated in exactly the same way as I did before. You get this light ray operator integral over u ju, and its action is also just universal. And so you end up getting all the soft theorem exactly.
Then you needed UA, right? UA.
I don't need that anymore. I've already done that by doing this expansion, which is inherently using both regularity and equations of motion. I've already related FUR to a radiative mode right here. So okay. So, and the last comment, what symmetry is this? This is it's almost easy to see for the leading one at least that this is gauge symmetry. Because what is the chart for gauge symmetry?
So the matching condition you're talking about?
Yeah, the matching condition I'm now going to show is the statement of symmetry. This is very easy because what is the charge for gauge transformations? The charge for gauge transformations is just integral on a surface sigma. On a Cauchy surface sigma is just the integral over the boundary of sigma of epsilon times times star f. And so if I simplify this for scri plus, the boundary of scri plus is scri plus minus. You should really think of sigma has to be a Cauchy surface. Scri plus by itself is not a Cauchy surface. It's scri plus plus I plus, and the boundary of these two things is just scri plus minus. So it's an integral over scri plus minus with r to the d, this coming from the metric. Then there's this epsilon, and then I have to evaluate star f along the direction of the sphere, which works out to be FUR. In d plus 2 dimensions. Remember the metric is du dr plus r squared dx squared. So there's a metric factor from there, and then star f. What I need to compute is star f along these directions, which is, and this thing is just equal to f ur times epsilon. And then I need to take limit r goes to infinity, because the boundary is square plus, and that's exactly that. So that this is exactly integral epsilon f ur d. So this is the charge on square plus. And if I take this equality, epsilon is arbitrary function. So this is this charge induces the gauge transformation A goes to A plus d epsilon. Epsilon is any arbitrary function.
Epsilon is an arbitrary function on the sphere or sphere times u?
It's a function on the boundary of sigma. Its value inside sigma is irrelevant because it doesn't contribute to the charge. So in particular, because the boundary of sigma in the case of square plus is just the sphere. So it's only a function on the sphere. You can extend it to square plus any way you want. It doesn't really matter. And so basically the fact that I'm setting these two equal, I can just multiply on with any function of x on both sides and then integrate. So then what I get is just q epsilon on square plus is equal to q epsilon on square minus. The antipodal identification is automatic because of the choice of coordinates. This x is naturally suited. So x equal to 1 on square plus, if that's the north pole, then x equal to 1 on square minus is the south pole. And so then when what do I mean by putting this into an S matrix? It simply means that the statement is
so physically this antipodal thing is that
is this a ray coming in from south pole goes and hits the north pole. That's all. And so that's it. That's the symmetry. There's also another symmetry which
so why is so you're taking of the consequence of non-trivial consequence of symmetry to be matching near the spatial infinity,
yeah.
right?
Yeah.
And this is just trivial matching of the charges here and near the time like infinity. That's because you are assuming nothing happens.
Yes.
Because of symmetry coming from there.
Yes. When I have massive particles, then you have to include those terms, and that has also been studied. You include those terms, and you get contributions, and they give you the corresponding soft factor for the massive charges.
Why is the massive? Why is it that when I have massive particles, I have to do this?
Well, massive particles. The point is that when I have only massless particles which travel in the null direction, I can consistently assume that all the massive massless particles reach here at some time slice here, and then beyond this everything is just vacuum. But if I have massive particles, then they reach here, and then so they radiate for all time, keep going. So you can never assume that the field strength is 0 up at that point. Okay, I think I'll just stop there. So anyway, so I think the just in conclusion, in odd dimensions, in addition to equations of motion, one needs to assume regularity and impose constraints of regularity to actually show that all of these things match. You in fact also did have to do, in principle you did have to do that also in even dimensions, but we were lucky in that those extra terms that one needs to add to ensure regularity don't affect the even dimensional story. So yeah, that's why it all worked out previously. Thank you. Yeah, sorry for for going way over time.
Any questions at ICTS?
Conceptually, how to think of
Yeah, I had.
Yes.
Yeah, go ahead, Toga.
I had about 2-3 questions. Okay.
Yeah.
So the first question is about this particular transformation and the charges. So what is so you're saying that you can take these charges and construct some analog of super transmissions on in the higher dimension, even in odd dimensions? Is that a statement?
Yes, so we can certainly construct everything in the gauge theory case. The gravity case is something I'm currently working on, so I haven't. We don't have all the technical details sorted out yet. But in the gauge theory case, you can construct all the charges on Scri plus in odd dimensions. Yeah.
Yeah, so you can construct the charges, but I'm just trying to understand whether, like in the odd dimensional case, it was local. is there a local transformation that that one can do? Because the f you had an integral, right?
Yes, yes, it's not local on the sphere.
And
And this has to do with the fact that Huygens principle sort of delocalizes the field. You have to, in order to, for instance, obtain the value of the field strength at a point x on the sphere, you have to integrate over the entire sphere to see what's going on.
so would you say that the take-home point then is that in odd dimensions you can have the soft theorems and the probably charges associated with them, but in a certain sense the charges are non-local, in the sense that the currents are non-local. Is that way to interpret these expressions that you wrote down?
Okay, you have to say non-local in terms of what? Yes, they are definitely non-local in terms of, for instance, the creation annihilation operators. So you have to integrate over the creation, which is, yes, agreed. That was not the case in even dimensions. It was local even in terms of creation annihilation operators. But I think the physical things, if I was thinking from a holographic perspective, the operators in the dual theory, the physical operators are the currents. So those things are, then what the correct statement would be is that the creation annihilation operators are non-local in terms of the current operators, which I'm defining as being local from sort of a holographic perspective. Is that?
Yeah, so basically there's no like in some sense the symmetries are not generated by one soft graviton, but as that kind of
Yes.
one soft photon in this case, but a soft photon cloud.
Yes,
which
very
is
good.
kind of in some sense irreducible to simple photons.
Very good. That's exactly right. Let me just rephrase, but you've already said it. If I have in even dimensions, if I have a graviton that goes and hits a point on the sphere, it induces a large gauge transformation on only that point. In even dimensions, if I have a graviton that hits a certain point, it induces a transformation on the entire sphere.
Odd dimension.
In odd dimensions. In odd dimensions, yes. Yes.
Yeah. Okay. So the thing that I'm worried about is that then the corresponding statements, like for example, in the soft photon case, there's in 4 dimensions there's a Cockney algebra, kind of thing. I mean, the question of what is the algebra of the currents, and so on and so forth. It's not quite clear to me because these are integrated over. These are not like really local objects. So. Algebra of currents and charge. Is there a simple algebra of currents in this case, or you don't think there is such an algebra? Or,
I haven't. I haven't studied it. I mean, naively, I would guess that yes, it would be very non-local. So maybe there is no nice algebra, but I don't know. I can't say. So there's oftentimes several cancellations do happen. The algebra, I haven't studied. In even.
Okay.
Well, I've not really talked about two charges, right? Algebra of charges requires you to insert two charges and then see. I've only talked about what
but
the rough.
You make statements like there is this super translations and so on. So some closure of algebra, this kind of.
Yeah, but that was in 4 dimensions and certainly in even dimensions. That there it closes, and that also statement is nice. But I suppose the interesting thing now that in odd dimensions it looks like there's some non-locality involved. Do you still even have some nice local?
Okay.
I suspect, in fact, I suspect not, but it hasn't been worked out.
Okay, so my final question, which is about the statement that somehow here what it matters what happens in the interior.
Yes.
You have to improve the regularity condition to really get this relation. So I was wondering, let's say, does it mean that it matters what the state is in the interior? For example, if I have a black hole in the interior, then the soft theorem change. Is that how I should think about it? I'm trying to understand the statement about how the interior matters in odd dimensions in a way that it does not the soft theorems in the even dimensions.
The interior definitely matters, but I think it also matters. In the example of, for instance, the black hole, it also matters for even dimensions, because then you do have to understand what's happening in the far future, because you have then that's connected to a black hole horizon, and then you have to understand what's happening in the black hole. So things that are falling inside the black hole will also contribute to the S matrix. So in
Yeah,
principle,
but-
so that's how the interior would contribute in even dimensions, and then in odd dimensions for sure, because in order to learn regularity, you need to sort of go all the way inside. Then it will matter what the geometry is inside.
So, but in even dimensions, you have the Huygens principle, which means that like whatever is coming out of the black hole or something, you can just look at the immediate vicinity of the like asymptotia
Yes.
probably and say something. But here like is the statement that the odd dimension, because of the failure of the Huygens principle, there's an afterglow of the states inside,
Yes.
which affects asymptotia. Is that a way to understand what you're saying? I'm just trying to.
Just want to first make the comment that in even dimensions, the interior also does matter. So even if it's true that it localizes there, the point is that Scri plus, for instance, in the example of a black hole, Scri plus is not a Cauchy surface. So it was crucial that it's sort of a Cauchy surface for us, because you actually have to integrate over the entire Cauchy surface to really reproduce all of the correct formulas and capture all the degrees of freedom. In the presence of a black hole, you also have the horizon. So I have to integrate over the Cauchy slice, a Scri plus, and the horizon, in which case all the interior states, whatever is happening inside the black hole, will also be crucial in trying to set up a soft theorem of some sort. And in odd dimensions, I think the same thing happens, but in a very different, physically in a very different way, because what's happening in odd dimensions, if you look at the radiative mode, it's just constant along the entire Cauchy slice. So it seems if it's entirely constant, then where is the information about the interior states coming in? And I think it's coming in because of the way you said it. Instead of Scri plus telling me about the interior states, which is connected to the horizon, it's the regularity that's telling me about the interior states. Is that too confusing?
Okay.
I think the interior does matter. I think the interior does matter, but I think it matters both in even as well as in odd dimensions. But I think in qualitatively different ways. Yes, sorry, go on.
So I was actually going to ask exactly the same question as Loga's last question. I was going to ask it in the following language.
Yeah.
Suppose I had some solitonic solution inside, no black holes, and I computed the analogues of the Bessel functions, just solve del square phi is equal to 0.
Yeah.
Now, will the coefficient, you had this very particular relationship between the leading fall off and the next leading fall off. Will that change because of what's happening inside?
That will definitely change. That will depends on how strong. Yeah, as long as it affects sufficiently far.
So then in electromagnetism, this looks universal because nothing happening changes because of the linearity of electromagnetism.
Yeah.
Right. I mean, the radiation is always propagating freely, no matter what else is happening. But what about in gravity? In gravity, when you start scattering, some high order, effectively the radiation is propagating in the background of what you've scattered.
Yeah. Yeah,
so
exactly.
Gravity in odd dimensions, it sounds unlikely you'll get a universal answer. I mean, even if you're doing scattering in flat space.
Yes. Yeah, but the same thing, even in even dimensions, you won't get a universal answer because you need to use equations of motion to go all the way down to the Coulombic order, and there you can get all sorts of contributions from the details of what's happening in the bulk.
So are you saying that these things are not, that there is it works to some order perturbation theory? So in the gravity case.
Also, there was a comment about this massive particles, right? So, in addition to that issue, there is radiation coming from whatever is inside. That also needs to be taken care of, right?
What do you mean? What is inside?
I mean, if the interior is not empty,
you have
stuff there. Then if there's propagate on that wall line there, that will true.
Then we need to talk about what's happening at I plus. Because after all, as I said, we need to talk about a full Cauchy slice. Scri plus is only a Cauchy slice if there are no stable massive particles. If I have massive, then I need to include I plus.
But let's simplify it. Let's say you're only scattering gravitons.
I understand. Yeah.
When you scatter gravitons for a while, something is created.
Yeah.
It changes space-time inside significantly. So another graviton that's passing through.
I agree. The soft theorems.
No, but that sounds worrying, right? I thought these were supposed to be exact statements. So that doesn't seem to fit what I thought.
No.
Exact statements is one software.
But this is only in odd dimensions the issue.
No, but also in even dimensions.
He's saying also.
Because
but the relation that you pointed out was specific to the odd dimension.
Yeah. So I use regularity to fix things in even in odd dimensions, which clearly you need to know stuff about what's happening in the interior. But also in even dimensions, the coefficient I'm interested is FURD, whereas the radiative mode is something at order d over 2. So I need to use equations of motion to really go all the way down to which is like, so it's sufficiently subleading. So, and in order to reach that subleading stage, I need more and more information about what's happening in the interior. So in that sense, even in even dimensions, there's some imprint of the details of the interior.
Yeah, so I'm probably saying it wrong, right? Because I keep hearing these statements that these are exact statements.
Yeah.
But why am I saying
Perhaps it might be, so as it actually does often happen, perhaps what it is that even though it affects all the way down, by the time you reach scri plus minus, I think maybe this is the statement. You can't have any finite energy non-trivial physical configuration in the bulk, which can in any non-trivial way affect what's going on at scri plus minus, because that's essentially causally disconnected from every point in your space.
So did you need along all of scri plus to use?
Well, I was integrating in all of those things, but the matching condition is coming only from scri plus, from scri plus minus.
Right.
So if by some way I manage to compute what the value of the field strength at scri plus minus, then I'm really done. I don't need to integrate and all. That was a step to compute things. And so since that's sufficient, that's like so far away from, that's causally disconnected from basically most of your space-time. There's nothing you can do with any finite energy configuration in the bulk that could possibly affect the fields out there.
So I probably understood things wrong. Let me ask again.
Yeah.
I understood the argument in 2 steps. First, these 2 things match.
Yeah.
And then you extract physics from that by integrating that over scri plus and scri minus.
Yes.
And I thought in that second step to extract the physics,
Yes.
you needed to use these.
Yes, but what I'm saying is,
Yeah, in getting
Yeah.
the actual relationship that is going to be interpreted as soft photon theorem, you needed to use this relationship on not just there but everywhere.
Yes. But what I'm saying is that I mean, it seems to me it has to be that whatever those contributions are, they have to cancel each other out, because at the end of the day, yes, I'm integrating and then I'm pushing it out into the bulk by doing regularity and whatnot. But at the end of the day, all I need is the value of the field at scri plus minus. If you just hand that to me, then I don't need to do all of this stuff.
Yeah, but the translation of the value of the field at scri plus minus to what
to the
looks like a soft photon theorem.
Yes.
Look like it depended on this detail, right?
Certainly.
And
I agree.
okay.
Yeah, I agree. Actually, I don't have a good answer to that. Yeah, they do say that it's perhaps. It perhaps is only true for sufficiently weak solutions, because for instance, when Weinberg derived soft graviton theorem, he assumed translational invariance and Lorentz invariance.
No, but
right? So you can't have
arbitrary scattering processes. So is this about a non-perturbative statement about scattering processes or not?
Well, the derivation is perturbative.
But every order in perturbation theory. Maybe that's enough.
More or less.
Maybe.
Yeah.
Maybe that's enough. Maybe I need some sort of iconal kind of resummation for to violate it. I'd have to think. Okay.
Yeah, but that's a very good question. I haven't. My suspicion is that it shouldn't matter. At the end of the day, things should really cancel out, and it is universal.
Yeah.
I don't see how.
Okay.
So, yeah.
Any more questions? ICDF?
Okay, no further questions.
How do the asymptotic symmetries get affected when you have multiple particles going soft? Is it something significantly different?
No, they're the same. Just like they're 2 charges, 3 charges, then you have multiple particles. Yeah.
And like memory check in 4 dimensions is just a Fourier transform of soft theorems.
Yeah.
But in soft theorems, as you said, it generalizes very easily to higher dimensions.
Yeah.
So what's the problem in just taking it?
Well, the Fourier transform is non-analytic. Like you can take 1 over p squared, but the Fourier transform of 1 over p squared is completely non-analytic in odd dimensions, but is very nice in even dimensions. So that's So then the particular mode that is responsible for memory happens to be constant. So which basically means that there can never be a DC shift. It will just be and whatever wave passes by, and then it will come back to its original point. That mode is just fixed. So it's certainly not, it's not that memory. Maybe there's some other definition of memory, some other imprint of the fact that the wave has passed by, but that has not been understood.